The data collected in the open circuit voltage testing that we just looked at, those 4 different test scripts with 2 major steps each, that data will ultimately allow us to compute the coulombic efficiency of this cell and also the open circuit voltage of this cell at different temperatures. I already mentioned some of this, but let's be careful and go over in detail some of the subtle points in being able to evaluate the data if especially the test temperature is not 25 degrees Celsius. It might be handy to have your notes open to the previous section as I go through here, because I'm going to be referring to different step numbers in those testing scripts, and for you to be able to compare back and forth to what I'm talking about. So in the first test script, we start with a fully charged cell. It's at 100% SOC before I begin. And in step 1, there is a rest to soak the cell at the desired temperature. And at the end of step 1 and before step 2, the cell is still at 100% state of charge because it's been resting. I'm going to assume that the self-discharge rate of the cell is negligible, which it usually is for a lithium-ion cell, assuming that my testing is done without a huge delay between the different scripts, as it would usually be the case. So I start with a fully charged cell, I rest for 2 hours, I soak at a different temperature, I'm still at 100% state of charge, but the voltage of the cell, the terminal voltage, will no longer be Vmax because open circuit voltage is temperature dependent, and I'm going to find a different value. Step 2 discharges the cell slowly down to Vmin, and at the end of step 2, the cell will be at 0% state of charge only if the test temperature is 25 degrees Celsius, because again, OCV is temperature dependent, and Vmin is going to specify the 0% SOC point only at 25 degrees. So at other temperatures, the actual state of charge at the end of step 2 may either be above or below 0% SOC of this cell. Then at step 3, I have a soak at 25 degrees, and at step 4, I'm going to discharge down to 0%. This here is the wrong step number. This should be 6. Step 5, we soak at the test temperature, and step 6, we charge at a constant current rate until the terminal voltage equals Vmax. And the cell will be at 100% state of charge at the end of step 6 only if the test temperature is 25 degrees Celsius, because again of this temperature dependence of OCV. And Vmax is that definition only at 25 degrees Celsius. So at other temperatures, the actual state of charge may either be above or below 100% at the end of step 6. So that's why I have not only OCV test script 1 and test script 3, but I also have script 2 in between them and script 4 after them, because those scripts operate at 25 degrees Celsius and they bring the cell to a known voltage which corresponds to a known state of charge, so I can calibrate whatever measurements I get from scripts 1 and 3. So we have to process the data carefully. We have to collect the data carefully, as we've described. We also have to process the data carefully. First, we look at what do I do with the data when the test temperature actually is 25 degrees C. And we always run one test at 25 degrees C in order to be able to compute all the results that we need. And this is the easiest case to perform because all 4 test scripts, all 8 steps, are executed at 25 degrees. No other temperatures are involved. And because voltages Vmin and Vmax are calibrated to 25 degrees C, the net ampere hours discharged over all steps equals the total capacity of the cell Q. The net ampere hours charged over all the steps turns out to be slightly higher than Q, the capacity, because the coulombic efficiency of this cell is not perfect. And this allows us to compute the coulombic efficiency of the cell at 25 degrees Celsius to be eta, evaluated at 25 degrees Celsius, equals the total ampere hours discharged in all steps at 25 degrees divided by the total ampere hours charged in all steps at 25 degrees. And this is going to be Q, and this here is going to be greater than Q, and that gives me a quotient that is going to be less than 1, so less than 100% efficient. If we have a test temperature that is different from 25 degrees, we must follow a somewhat different approach. We don't know beforehand the cell state of charge at the end of step 2 and at the end of step 6, but we do know the cell state of charge to be 0% at the end of step 4 and to be 100% at the end of step 8. And we use this information to compute first the coulombic efficiency at the test temperature T. And the coulombic efficiency then, eta at test temperature T, is the total ampere hours discharged from the cell divided by total ampere hours charged at temperature T, and then minus the efficiency at 25 degrees, which we just computed, times the total ampere hours charged at 25 degrees divided by total ampere hours charged at the test temperature T. You can go through that and figure out why that would be. You basically would rewrite this expression to solve for the total ampere hours discharged, multiplying both sides of the equation by total ampere hours charged at temperature T, and call that total ampere hours at T, and you would get total ampere hours discharged as eta of T times total ampere hours charged at T, then plus, bringing this to the other side, eta 25 times total ampere hours charged at temperature 25. And that's how the efficiency calculations work. We are assuming, by the way, that the coulombic efficiency of a discharge is always 1, which allows us to solve for the charging coulombic efficiency. I performed this test for a lot of different cells for the purpose of building this course reader and the text. I chose 6 different lithium-ion cells. Some of them are big, some of them are small, some of them are laptop size, some of them are vehicle size, different chemistries, but all lithium-ion cells. And have done this for temperatures from minus 25 Celsius up to 45 Celsius in steps of 10 degrees Celsius, and tabulated the results of the coulombic efficiency calculations and drew the graph that we show here. If you look at the scale, in all cases we see a coulombic efficiency above 98%. And that is very typical of a lithium-ion cell, especially when I am charging and discharging at a slow rate. If I use a higher rate of current, we find that the coulombic efficiency actually gets worse. And I'm not going to get into that here. That's not part of the model that I developed, but if you want it to be really accurate, you would perhaps have an efficiency relationship that is also a function of the magnitude of current. And that gets to be somewhat trickier to work with. But for a slow rate, we have very high coulombic efficiencies, usually above 99%. Some of those slightly less efficient cells are laptop cells that were not brand new, and so they were from older technology and older cells where the aging had caused some decrease in the efficiencies. Also, the efficiency should be less than 1, but at least in one case here, maybe 2, maybe there, and maybe there, we see that the coulombic efficiency calculation gives us a value greater than 1. So do I have a cell that works better than perfect? And the answer is no, I don't. I have an instrument that is making measurements on the cell where the instrument is less than perfect. And the instrument is calculating the integral of the current dt to give me my ampere hours charged and discharged, and any errors on this current sensor are getting integrated over time, and so there is really some uncertainty to how, because of random electrical noise, is this integral really accurate? And the uncertainty grows with time, which is typical. That's how the integral works. And because of that, my Coulombic efficiency calculations are not going to be exact. I would probably need to do these over again several times in average results if I really needed a very good value to try to average out the uncertainty in the integration of the current sensor. So the Coulombic efficiency here is not more than 100%, but the calculations that we just went through would compute that value there. And we can compensate for it in a very simple way by limiting the efficiency to be no bigger than 100%. And that isn't such a bad thing to do. Or I could repeat the experiment. One thing to note is that the step 1, script 1 is 2 hours for step 1 plus 30 hours for step 2. Script 2 is 2 hours for step 1 plus an uncertain amount for step 2. Let's just call it 2 hours. Script 3 is 2 hours plus 30 hours, and script 4 is maybe 2 plus 2 hours. So I got 2, 4, 6, 8, 10, 12 plus 60. I've got 72 hours of testing at minimum to get the data for a single temperature. And unless you have a highly automated laboratory where you can control the thermal chambers under computer control at the same time as you control the test scripting, if you don't have that, you're going to have to start script 1 and then come back in a day and a half and reset your thermal chambers manually and then start script 2 and so forth. I find that these tests take on the order of 1 week per temperature per cell that I'm working on. And so if I've got 1, 2, 3, 4, 5, 6, 7, 8, in order to get the data for this picture here, that took 2 months. 2 months of real time in order to get that data. So you don't want to redo this too many times. You have to be very patient whenever you're collecting data from cells because they just operate as quickly as they operate, and there's not much you can do about speeding that up.